Hello and welcome. Introduction. In this video, I'm going to show you how to program the TM4C123GH6PM microcontroller timer using assembly language. Now, before going into the details, let me show you the full listing of the program. The program full listing. Okay, so here is the full listing. At this point of the video, I'm just going to show you the listing. In a few moments, I'll explain it in more detail. So this is the beginning of the program. So here I define the peripheral base addresses, and here are the peripheral offset addresses. Declare here, and here I define the bit masks being used in the program, and here is the main function or main routine, our main program. And here basically I call this subroutine init GPIO. Here I call the subroutine init timer. Here I send the program into the loop, toggling the LED. And here down here, I have the init GPIO subroutine here. And then here I have the init timer subroutine. Like I said earlier, the details will be coming on very soon. And finally, but not least, this is the subroutine for toggling the LED. And so that's it for the full listing. The program. So from here, I'm going to explain the program in detail. Let's get my pointer. All right, so we start off with this part of the program. So this area directive defines a section in memory where the code or data will reside. And here my code is the name of that area that I talked about. All right, so this is just a name, and code indicates that this area is meant for executable code, and read only specify that this area is read only, and export here is a directive, and here underscore main is what we call a symbol which says that this is available to other modules or files. Okay, so here I define the peripheral base addresses. So the first one is this one here, SYSCTL underscore base, EQU, hexa, the 0x here denotes hexa, 400 FE000. This is in hexa, and this is the base address that is assigned to this SYSCTL underscore base. And this is the base address for the system control block. And I've taken this base address from page 231 of the datasheet. Next is the GPIO F. F here denotes port F underscore base, and this is being assigned a hex value of 40025000. 000. And so this is the GPIO port F base address. And I've taken it from page 662. And if you go to that page, somewhere on the page, you will see this. And this is the base address being defined. And the third base address that I want to point out is the timer 0_ base, and that has an address of 40030000 hexa, and I've taken it from section 11.5 of the datasheet entitled Register Map, and you'll find the timer 0 base address on that in that section. So here are the peripheral. Let me get my. So here are the peripheral offset addresses, which I defined here. I'll show you where I got all these offsets from the datasheet. The rest you can find them in the datasheet. So let's look at this RCGC GPIO. That is the run mode clock gating control register for GPIO, and the offset is 608, and you can find that from the datasheet page 340, and the offset is on that page. You can see that pointing out to you, so you can refer to the datasheet and check it out. So for the rest, I'll just read the offset to you. So it's RCGC timer, and the offset is 604. The GPIO underscore AFSEL, the offset is 420 hexa, and the GPIO underscore DIR is offset is 400 hexa, and the GPIO underscore DEN is 51C hexa, and the GPIO underscore data, the offset is 3FC. Okay, so these are the offset values for the timer. So this is the first one. This is the general purpose timer module control register, which is the GPTM-CTL, and it has offset value of 00C hexa, and I think you can find this on page 737 of the datasheet. And yeah, so this is the timer underscore CTL, which is this GPTM-CTL. So the rest of the offset value, so this is timer underscore CFG. CFG is configuration register, and the offset is 000 hexa. And this is timer underscore TAMR. That is the timer A mode register, and the offset is 004 hexa. And timer underscore TAILR, that is the timer A interval load register, and the offset value is 028. And timer underscore RIS, RIS is raw interrupt status register, and the offset is 01C. And then we have timer underscore ICR. ICR is interrupt clear register, and the offset is 0 to 4 hexa. Okay, so here I define the bit masks. So let's start off with the GPIO F_enable that has a mask value of 20. That is, this mask is used to disable the GPIO of port F. Then pin _2 is 04 hexa. This is the blue LED or PF2 on the launchpad board. Then timer 0_disable has a mask of 00 hexa, and this is to disable timer 0. And then timer 0_enable, that is 01 hexa. This is to enable timer 0. And then timer _periodic mask is 02. This is to set timer 0 to a periodic mode. And the timer _count_down, which is 10. This is used for checking the countdown of the timer. And here we have 2BL instruction. Basically, this is branch with link. Basically, this two instructions here, basically this will initialize or call the subroutine init GPIO here. This subroutine will initialize the GPIO, and init timer subroutine will initialize the timer. And here we have the loop. All right, this is a if you recognize this, this is the branch back to here. So this is an unconditional branch. So this will send this into a loop, and basically in the loop we branch to a subroutine called toggle LED, and this subroutine here basically will toggle the blue LED. Okay, so here is the init GPIO subroutine, or here we call it a procedure or prog. So this is the entire subroutine, and these 4 instructions here, the purpose of these 4 instructions is to enable the clock to the GPIO of port F. All right, so and let's start off with looking at this instruction. So this LDR R0 comma equal STYS CTL _base, that this has been assigned this hex value, which is the base address 400FE000. So this has been assigned or declared earlier. And then we have the RCGC GPIO. This has been assigned hexa 608 earlier. Then this instruction here, all right, basically this instruction here, basically this will assign this value, all right, to or load this value into R0. All right, so R0, when we come to this instruction LDR R1 comma square bracket R0 comma hash RCGC GPIO close bracket square bracket, basically this one here is a load instruction. All right, so this is a load instruction, and what it does is it first of all computes the effective address. What that means is, remember in R0 we already stored 400FE000 hexa. All right, so that is done here. So the R0 will have this value, and RCGC GPIO has been assigned 60 hexa earlier. So the effective, so this instruction here will first compute or work out the effective address. What that means is it will take this value here and add this value to it, and the result is 400FE608. So that is the effective address. So what this instruction will do is it will load the current value at this address. All right, load the current value at this address into a register R1. All right, so that's how it does it. So next we come to the OR instruction, ORR instructions, and this GPIO F_enable has a value of 20. This is the bit mask which was assigned earlier. All right, and the ORR or logical OR performs a bitwise OR operation between R1, all right, the contents of R1 with the value 20 hexa. So the bitwise OR operations between this one, this value, and the contents of R1. Now next is the store str instruction, the store instruction. Now again, RCGC GPIO, remember it's the same here, that has been assigned this value, all right? And basically the store instruction, this str is a store instruction and identical in the sense that it first of all work out the effective address. Now the contents of R0 is actually this value. This has been loaded into R0 at this point. So that has this value. So this value plus the 60. Basically, effectively, this is identical to the load instruction here. So the effective address is also at this point 400FE608. But the action here is it will write or store the value in R1 into this address. All right, so now it will store this str here, will store the value that is in R1 back to this address. So in other words, the str instruction and the LDR instruction here, they are basically the opposite. Okay, so the next three instructions here, basically these instructions disable the alternate functions of the GPIO-F or the GPIO of port F. Now, so this GPIO F_base, this has been defined earlier, and it has a value of 40025000 hexa. This is an address. So this value gets loaded or copied into R0. So remember, at this point, R0 will have this value. And then when we move to this MOV or move instruction, basically this instruction here will copy this value 00000000 hexa, copy this value into R1. Now, when we come to this store instruction, which we have covered earlier, but we'll go through it. So this str instruction here, before we do that, this GPIO_AFSEL has been assigned 420 hexa, defined earlier. So the str basically is, as I mentioned earlier, is similar to the one that we have encountered earlier. So this is a store instruction. All right. So first of all, it works out the effective address by adding this value, the base address, GPIO base address, to this 420, and then the effective resultant address is 400.25420 hexa. So it will then store the value in R1, right? Whatever is in R1 will str here will store that value in R1 into this address here. Now we come to this next two instructions here. Basically, these two instructions enable the GPIO pins of port F as output. All right, so this MOV instruction here will copy this value. This value has been 04 hexa has been assigned to pin _2. So we'll copy this value into R1, register R1. Then we come to the familiar str R1 comma square bracket R0 comma hash GPIO _dir close square bracket. Now this GPIO _dir has been assigned 400 hex defined earlier. So store instruction again here works out the effective address, all right, which is already in the what do you call R0, which is this one here. So the effective address basically is this value, all right, which is this one added to the base address, giving us 400 FE400 hexa. So the store instruction basically will store the value in R1, all right, into this address here. Basically, this 3 str is identical in its operation. Okay, so this instruction here basically enable the GPIO pins of port F as digital functions. And this here, as we've seen earlier, is a store instruction, and the GPIO _ DEN that has been assigned 51C hexa. This been defined earlier, and the store instruction needs to work out the effective address first. So the effective address basically is this value, which is this one here, the GPIO F _ base. All right, that is 400.25000 hexa, add 51C hexa. So that would give us an effective address of 400.2551C. So the store instruction would then store the current value, whatever's in R1, the current value in R1, store that into this location. And then finally, we arrive to this two, well, whatever is the instruction. This is a directive, END, end procedure or end of subroutine, well, ENDP. And this instruction here basically is to branch, BXLR will branch or return the control back to the main program as seen earlier. Okay, so here is the init timer subroutine or procedure prog. And if you notice very quickly that these instructions are identical to the init GPIO subroutine that we've seen earlier. All right, so let's start off with this, with these instructions here, and it's in fact these are identical to the init GPIO subroutine. So here, these instructions here will enable the clock for timer 0. All right, so this SYSCTR underscore base, that has been assigned this address or value 400FE000 hexa. All right, so this value will be copied into R0. And this RCGC timer, that has been given a value of 60 hexa earlier. All right, so, and this LDR instruction, load instruction, basically, it first of all needs to work out the effective address, which is basically 400 FE000, which is this one, and then add 6004 hexa, and the resultant or effective address is 400 FE604 hexa. All right, so basically this will store the current value in this location, here 400 FE604 address, store that value, whatever is stored here, into R1. All right. And next, we have the OR instruction, and this timer 0 underscore enable, that has a assign a value 01 hexa, and the ORR or logical OR instruction perform a bitwise OR operation with the contents of R1 with this value. All right, that's the purpose of this instruction. And then next, we have the STR instruction or the store instruction. So here, it will work out the effective address. All right, to do that, it will take this value and add it to the value, this value here, which is basically 400 FE000, add 604, and then the effective address would be 400 FE604. All right, and then the store instruction, what happens is it will take this value, whatever value there is in here, all right, R1, and then store that into this address. So opposite of this LDR. Okay, so the next three instructions here, basically these three instructions will disable the timer before initialization. And quick reminder, timer 0 underscore base was assigned this value, and then this LDR instruction will copy this value into R0. All right, so next we have the timer 0 underscore disabled, that has been assigned 00 hexa earlier, and then that is copied with this move instruction. It will copy this value into R1. And then now we come to this store instruction. Basically, it will first of all work out the effective address here. And quick reminder, timer underscore CTL was assigned 00C hexa in the earlier part of the program. So here, as I mentioned a few moments ago, this part here will work out the effective address, which is basically the timer 0_base address, which is 40030000, add the timer _CTL, which is basically 00C hexa. So the effective address would be 40030000C. All right, so the store instruction will then copy whatever the current value is in R1 into this effective address. Next, these instructions, these two instructions here, basically the purpose is to configure the GPTM, that is the general purpose timer module configuration register. So the first instruction here, this MOV instructions, copy this value into register R2. And we come to this store instruction here. So this timer _CFG is assigned this value 00 hexa. This has been defined earlier. And a quick reminder, the R0 contains this address, which is the timer 0_base. All right, so R0 would have this address. So the store instruction calculate the effective address, basically taking this, adding this value, which is CFG, to this address. So the effective address would be 40030000. And the store instruction will copy the current value in R2 into this address. Next, we come to these three instructions here. Basically, the purpose of these instructions is to set the timer to the periodic mode. And timer _TAMR is assigned this value, all right, which is 004 hexa. This has been defined earlier. So LDR will first of all work out the effective address. All right, so the quick reminder, the R0 here was assigned 40030000 hexa. So at this point, R0 has this value here. So when the LDR work out the effective address, it would be this, which is this one here, add 004. All right, so the effective address would be 40030004 hexa. So it will then copy the current value in this address, all right, the effective address, into R1. Now, then we come to this OR instruction, timer _periodic was assigned this value earlier. So the ORR here instruction, the logical OR instruction, will do a bit wise OR, perform a bitwise OR with the value in R1 with this value here. And then we come to this STR instruction, the store instruction. So first of all, it has to work out the effective address. Now, if you look at this and look at this, they are identical. So basically, the effective address would be this one here. So what this str instruction would do, it will store the current value in R1 into this address. All right, sorry, it stumbled there a bit, into this address. So store the current value in R1 into 400300004 hexa. Next, these two instructions here will basically set the countdown mode, and timer underscore count underscore down, that is been assigned this value earlier. So the ORR instruction will perform a bitwise OR operation between R1, the contents of R1 with this 10 hexa. So the logical OR operation will be performed between this value and the value in R1. And then store our familiar store instruction. So first of all, it needs to work out the effective address, right? So R0 was assigned 4003000 earlier. Basically, that is the address of the timer 0 underscore base. So that is in there. And timer underscore TAMR basically it's been assigned 004 hexa. So the effective address is this. All right, you add this value, which is 400300000, add 004. Effective address is 400300004 hexa. So the store instruction will then store the current value in R1, whatever is in R1, will store that into this address here. Okay, so we come to these two instructions here, and the purpose of these two instructions is to load this 50 decimal value of 50 million, all right, into timer underscore TAILR, which is the timer A interval load register. All right, so so the load instruction LDR will copy this value into register R1, and then to remind ourselves, timer underscore TAILR has been assigned this value earlier, which is 028 hexa. All right. Now, the store instruction here will first of all work out the effective address. All right. So, as a quick reminder, R0, register R0, has been assigned 4003000 hexa earlier. That is the timer 0 underscore base address. So R0 already contained this, and this timer underscore TAILR was assigned 028 hexa. So the effective address is basically this here at 028 hexa. So the resultant or the effective address is 400300028 hexa. And the store instruction will copy the current contents or the current value stored in R1 into this address. Okay, so the load value is calculated using this equation. So we want a time interval of 1 second. All right, so this is the time interval we want. And the system clock with the Kyle Microvision IDE is 50 megahertz. So if we substitute this value into this rearrange equation, then we get 50 million in decimal. Now we come to these two instructions here, and the purpose of these two instructions is to enable timer 0 after initialization. Now, timer 0 underscore enable, that has been assigned 01 hexa earlier. So the MOV or move instruction will copy this value, all right, into R1. Now, before we get into the str store instruction, let us remind ourselves R0 here has been assigned 4003000 hexa. Now, this is the timer 0 underscore base address. So that one is here, and timer underscore CTL, that has been assigned 00C hexa earlier. So the str store instruction will first of all need to work out the effective address, all right, which is this one here, 4003000 at 00C hexa, and the resultant address or effective address would be 4003000C hexa. So the store instruction now will store the current value of R1, whatever is in R1, copy that into or store that into 4003000C. And then finally, we come to this last two instruction. This BXLR will branch back to the main program or return to the main program. And E and the P marks the end of the subroutine or procedure or prog. Okay, so now we come to this subroutine toggle LED prog, and the purpose of this subroutine, which is the entire subroutine here, is to toggle an LED. All right, so these instructions here is to check if the timer has expired. All right, so that's the purpose of these instructions here. So let's start off with this LDR load instruction, and a quick reminder, timer 0 underscore base has been assigned this value earlier in the definition of the addresses for the base. So 4003000 hexa has been assigned to timer 0 underscore base. And what this LDR instruction would do is to copy this into R0. So bear in mind, R0 would have this value. Now, when we come to this instruction here, this load instruction, as a quick reminder, timer underscore RIS has been assigned 01C hexa. So in this instruction here, the LDR instruction will have to first of all work out the effective address. Now, as we saw earlier, R0 has this value, which is actually timer 0 underscore base. So to work out the effective address, so is this here, this address, add 4001C. All right. So you add the 2 and you get 40030001C. So that is the effective address. And the load instruction will basically copy the contents of the current value, whatever the current value is in this address, will be copied, loaded into register R1. Okay, now we come to this AND instruction here. Basically, this instruction will perform a bitwise AND operation on R1 with this immediate value. All right, the result of the AND operation is stored back into R1. All right, so the result of the AND operation you'll find it in R1. Now, essentially, this operation checks the least significant bit to see the least significant bit of the raw interrupt status register, the RIS. Now, if this bit is set to a 1, all right, it means a certain condition, for example, an interrupt or any other event has occurred. And next is the test instruction, and here the instruction is used to perform a bitwise AND operation with itself. So it's actually an AND with itself. This will update the conditions flag based on this test. However, the result of the AND bitwise AND operation is not stored at all, it's disregarded. The only thing that happens is that the result will update the condition flag. Now, this is effectively a way to check, or effectively a way to test the value of R1 to see if it's 0 or non-zero. All right, so you check the contents of R1 to see if it's a 0 or non-zero. Now, if the contents of R1 is 0, the 0 flag, all right, the 0 flag is set. Otherwise, it is clear. Now, next comes the BEQ branch if equals instruction. Basically, this will check the 0 flag set by the test instruction. Now, if the 0 flag is set, then the program will branch to the label AND toggle, which is this one here. So if the 0 flag is set, it will then jump to this part or branch to this part here. Okay, so these instructions here, these two instructions will clear the timer interrupt. And let's look at the MOV instruction here. Basically, this will copy the immediate value, this value here, into register R1. And then we come to this STR instruction, the familiar STR instruction. So first of all, the instruction will work out the effective address. All right, now timer underscore ICR has been assigned 024 hexa in the earlier declaration. So, and quick reminder, R0, which is this one here, that's 4003000 hexa. That has been assigned up here. So that R0 still retains that. So the effective address, all right, would be this base value here, the timer 0 underscore base value, add 024 hexa, and the effective address would then be 400300024 hexa. And the store instruction will copy the current value in R1, which is this one here, into this address. Okay, so we come to this 4 instructions here, and basically the purpose of these instructions is to toggle the LED. And let's start off with this instruction here. So GPIO F underscore base, that has been defined or assigned 400250000 hexa. So the LDR instruction will copy this value or load this value into R0. All right. So next we come to this LDR instruction. This is a load operation, and GPIO underscore data has been defined as 3FC hexa. So the LDR instruction will first of all work out the effective address here. All right, the quick reminder, R0 has got this value, location, 400250000 hexa. And the effective address basically is this address, or this address add to this address, which is 400250000 add 3FC, and the resultant or effective address would be 400253FC. So once the effective address is worked out, the then instruction copies the current value in this location into R1. Next is the EOR. That stands for exclusive OR. And pin underscore 2 has been defined as 404 hexa. So the XOR instruction performs a bitwise XOR operation between R1 and 04. And then we come to the store instruction, which we are familiar with this by now. So first of all, let's look at the value that has been assigned to GPIO underscore data. That is 3FC. That's been defined earlier. So the effective address would be, remember, R0 has this value 400250000. So the effective address would be this at this. So we have this 400250000 at 3FC, and the resultant or effective address is 400253FC. And the store instruction will then copy the current value or current content of R1 into this location. This is the store operation, and the LDR instruction is just the opposite of each other. Okay, and finally, we have here BXLR. Basically, this is branch or return back to the main program. And the word align here is an assembly directive that ensures proper alignment of instruction or data. And E and DP here signal the end of the subroutine or prog. And finally, E and D directive here marks the end of the entire program. Demonstration. Now for this demonstration, you will need the TM4C series launchpad board connected to your desktop or your laptop. Okay, so I've uploaded the code here, and so this is this part here. I've defined the base addresses, the peripheral base addresses, and then I define the peripheral offset addresses here, and here I define the bit mask used in the program, and here I have the main subroutine on the main program, on the main prog, and then here is the init GPIO subroutine, and here is the init timer subroutine. All this we've been through in details earlier, and then here is the toggle LED subroutine. All right, and finally the END end directive to signify the end of the entire program. So first thing, let me just go to project and then build the target. And as you can see, there are no errors or warnings, so we're good. Okay, so here is my hardware setup. Here is my launchpad board, and here is my USB logic analyzer. You don't need this for your purposes. If you have one, that's okay. If you don't have one, that's okay too. So the purpose of the logic analyzer is to show you the duration of the time intervals. All right, so this is my physical hardware setup. Okay, so here's the code that I have compiled earlier, and as you can see, there are no errors, no warnings, and my hardware setup is ready. My board, my launchpad board is connected to the laptop, but I need to switch it on. All right. Okay, so now my board is connected. So let me download the code to the board. Watch this part here. Okay, so it says erase done, programming done, verify, okay. So the program would have been downloaded. So let's pull this back up. And let me just press the reset button. As you can see, the blue LED on the board is now blinking. All right, so now we will proceed to the USB analyzer output. Okay, so this is the output from the launchpad board using the USB logic analyzer. So let us just measure the duration of the on state and the off state. So, all right, so here we go. And you can see it's 1 second, which is what we want. So let me just zoom in. You can see it's a 1 second on. Zoom out, and then let's measure the off state. And again, as you can see, it's 1 second off. So basically, the USB and logic analyzer confirms that the blinking rate or the flashing rate of the LED is 1 second. 1 second on and 1 second off. Okay, so that's it for this video. I hope you have found the contents useful. Thank you for watching. I'll see you in the next video. Bye.